We were discussing about this multi-carrier modulation technique, how it is advantageous, and how do you see multi-carrier technique in a frequency domain point of view. Let us now see the same ideas in time domain point of view. So you can see the signal in time domain and frequency domain, and multi-carrier method is more evident, it is more obvious in frequency domain. You can see that the whole bandwidth of the signal is divided into small substreams, and these substreams, they are orthogonal to each other, uh, and it's where you can see the division, how the bandwidth is divided among different small substreams. But in time domain, it is a slightly more complex thing happening, and you need to really listen to understand the concept of what is really happening in time domain of this multi-carrier modulation technique. Let us see that now. Before discussing the time domain point of view, okay, we are going to discuss the time domain. Time domain point of view of multi-carrier modulation. Before discussing this, we'll just see revisit the concept of coherence time. Okay, what is a coherence time? Let this be an a channel impulse response denoted by h of t. So coherence time. Yeah. The first, this is time. Now the axis is time. This is channel impulse response. H of t is channel impulse response. Channel impulse response. The channel impulse response is h of t, which means what is an impulse response? It is a response to an impulse, or it is the output of a system when there is an impulse input. Let's say that you transmit an impulse at the input. Okay, if you have a system here, yeah, you transmit an impulse input to the system. Here the system is wireless channel. So you transmit an input to the system, the output is h of t, which is the channel impulse response. And the channel impulse response, it basically it will look like you will have the first signal copy here. Let me draw with a different color. You will have the first signal copy here, and the channel will have the second signal copy. All this is due to the multipath effect, and the third signal copy, and you may have a number of copies after this, but you try to neglect all those because their signal power is very less, so those copies are ignored. You take only the most significant copies, and this is going to be your delay spread, okay, or it is a coherence time. So almost the signal is almost constant along this time. So this is your TC, which is the coherence time. Coherence time is the time over which the channel remains approximately constant. Coherence time is the time over which channel remains approximately constant. the channel doesn't vary with respect to time in this coherence time. After coherence time, the channel may vary its characteristics, but during the coherence time, the channel is approximately a constant. So that is the concept of a coherence time. And how you want the signal to be. You want the signal, the transmitted signal, uh, the time domain, the symbol time, the symbol time of transmitted signal, it should be greater than the coherence time. Should be greater than the coherence time of the channel. So why is this situation arising? That is what you are going to try to understand. Um, let's take the previous example. Let's say you have 6,400 bits per second, and you are suppose you are using a single carrier. So every symbol, so you have a number of symbols, x of 0, x of 1, x of 2, etc., etc. If you are using a single carrier, then every symbol is going through the whole bandwidth. Every symbol has this whole band, consumes the whole bandwidth. Let me draw the earlier figure, this figure. So you have the signal like this. So this is the signal frequency domain. The equivalent time domain will be, see, if this is some frequency, okay, some fixed frequency, then the time domain is going to be, let me make you understand this. Yeah, if you have the if you have yeah if you have a square like pulse in the frequency domain, then the time domain, at the time domain you will have a sync pulse. You will have the sync pulse, and the sync pulse will have some time duration. Suppose this time duration is denoted by t, and this is minus t, okay, and this let's say this is b and this is minus b. Then you have to know this relation, that this t, the time, this time duration is actually 2t, where this t is from 0 to t, this is t. This t is inversely proportional to b, the bandwidth of the signal. Always the time duration is inversely proportional to the bandwidth of the signal. If you increase the signal in frequency domain, then you will have a decrease in time duration of the signal in time domain. So that is idea. So you increase t, when t increases, then b reduces. Similarly, when b increases, bandwidth is large, then your time duration will be very small. From that idea, let me go here and say this. Here the bandwidth is large, the incoming bandwidth is b, it is having a large value. So the time domain, you will have the signal as a very small duration, very small time duration signal. Okay, it is going to be a very small time duration signal, right? But if you have a substream, let me just draw a substream here. Substream is having a bandwidth which is much less than b. that is Bn, and Bn is obtained by B divided by n, and this Bn is very small when compared to B. Mostly in most of the cases, n is a large value, so Bn is very small. As a result, it will the equivalent time. Let me draw that with another color. If you have this substream here, which is having a lesser bandwidth, then in the time domain here, in time domain, you will have the signal which has more duration, right? So in multi-carrier, you see, you are dividing this small substream. You're dividing the whole bandwidth into small substreams. So you will have signals with more duration in time. You will have signals with more duration in time. Now, how can you relate this with coherence time of the channel? That is what we are trying to analyze. You see, this is the channel impulse response, and you send one particular signal, and you have three copies at the receiver. So you have send an impulse, you have three copies. Then you send any signal, then signal will have three copies. And this copy is h of 0, this is h of 1, this is h of 2, right? H of 0, h of 1, h of 2, these are the channel coefficients in time, where h of 0 is the channel coefficient for the first copy. H of 1 is the channel coefficient for the second copy of the signal. H of 2 is the channel coefficient for the third copy of the signal. Okay, and let's say that let's take the another case, that let's take the case like the signal symbol time is less than the coherence time, and we'll see what happens. Let's take that case where you have the channel impulse response h of t, and you have this is the coherence time tc. So we are taking the case when the symbol duration which I denote by t is less than tc. Okay, let's say t is just this. Okay, this is t, this duration is t. Okay, like an example, it is actually the sampling period. This is t, right? In this case, t is less than tc, and you can see that what happens. You transmit the first symbol x0 like this. You are transmitting each of the symbols, and please note, when you transmit using a single carrier, your bandwidth is large. Okay, bandwidth is a large value, and your time duration is very small. Okay, the time duration of the symbol is small, and as such you can transmit a number of symbols in a particular amount of time. And you transmit the first symbol, that is x0. Okay, and let's see what happens at the receiver side. Let's see what happens at the receiver side. You have the received signal denoted by y of t. Okay. So you transmit x0 and x0 reaches the receiver as 3 signal copies. You have the first signal copy. It is going to be x0 into h of 0. You have the second signal copy, that is, let me give some space. Yeah. The second signal copy, and that is going to be x0 into h of 1, because it is a second signal copy and h of 1 is the second channel coefficient, or h of 1 is the gain of the channel in time domain in the second instant. And the third signal copy is going to be x of 0 into h of 2. All right. Now transmitting the second symbol, that is x of 1. Remember, the symbol duration is capital T, and capital T is only this much. Okay. You are transmitting these symbols continuously, which means you transmit the symbol x0 here, and the symbol duration is only t, which is same as the sampling period here, which is same as this duration here. So at this point, at this time, you will have the x0, x of 1 getting received. The first copy of x of 1 is getting received here, right? So let me denote that by another, denoted by red color. Okay. Yeah. Right. So you have x of 0, h of 1 at the second time instant, but the symbol duration is less, which means at this point of time you're also receiving the first copy of x of 1. And what is going to be the first copy of x of 1? First copy of x of 1 is going to be x of 1 into h of 0, because it is multiplied by h of 0, because uh, concerning x of 1, the first copy just reached here, and first copy has to get multiplied by h of 0, and this is h of 0, this is h of 1, this is h of 2, right? And you will have the second copy of x of 1 here. Okay, so plus x of 1 into h of 1, right? And in the next time instant you are transmitting x of 2, which is the next time instant. There's a third time instant. So you will have this here, that is x of 2, so plus x of, oh, sorry, so here you will have x of 2 into h of 0, and it goes on like that. And what do you see here? You see that there is inter-symbol interference. You see that here you have inter-symbol interference. So there is x of 1, x of 0, and here there is x of 1, and the two different symbols are interfering with each other. So you have inter-symbol interference, or ISI. In the third instant, you see the symbols x of 0, x of 1, and x of 2. They are getting added with each other, right? So you have inter-symbol interference. So when you have the signal time duration less than the coherence time, you have this problem of inter-symbol interference. How you could have avoided it? You could have avoided this by setting your symbol duration greater than the coherence time of the channel. If just think, if the symbol duration t was greater than the coherence time of the channel, then your x of 0 gets transmitted and 3 copies are received, and then the symbol duration is greater than the tc. So after this all the symbol copies are received, you will have the next transmission of the symbol x of 1. So in that case there won't be any inter-symbol interference. Okay, so you always want the symbol duration t to be less than tc. But what happens if you are in single carrier communication? In a single carrier communication, in a single carrier communication, B is very large. So B is very large means B is inversely proportional to the symbol duration T, and T is going to be very small. T is going to be a very small quantity, which means when T is very small, this problem happens. T becomes less than the coherence time of the channel, and as a result you will have this problem of inter-symbol interference. And it is a serious problem. You will not be able to recover any of the signals x of 0 or x of 1 out of this, right? So you have this problem of inter-symbol interference when you have the symbol duration less than the coherence time. And how can you avoid this? In yeah, another point I want you to notice, what I have written here, x of 0 into h of 1, which is the first symbol value y of 0, and x of 0 uh, h of 1 plus x of 1 h of 0, it is y of 1. It is a second symbol at the receiver, and the third symbol received at the receiver is this quantity y of 2, and this actually defines a convolution operation. You can see each of these values, it defines a convolution. I've written nothing but the convolution operation. We all learn that the input signal undergoes a linear convolution with the channel impulse response, and this is how you visualize it. This is actually a convolution operation happening here. Yeah, that's a point I want you to note. And how can multicarrier avoid this? In multicarrier, this is not the case. In multicarrier, your Bn, the bandwidth of each substream, is less than B. How is it possible? You divide B with n, and your bandwidth of the substream is much less than B, which means that your time is going to increase. You will time duration of the symbol is going to increase. You will satisfy this condition in such a way that Bn is less than the coherence bandwidth of the channel, right? So when you write like this, Bn is less than Bc, it means that 1 by Bn is nothing but it is proportional to 1 by Tn, where Tn is the symbol duration of each substream. It is symbol duration of each substream. It is less than 1 divided by Tc, coherence time of the channel, which means that Tn is greater than Tc, and you have this condition for 0 ISI, for zero inter-symbol interference. And that's an interesting point. What happens in a single carrier and multi-carrier in time domain? In a single carrier, just give me a second. Okay. In single carrier, what happens is that the signal transmission, it happens in very short pulses. Okay, you have very short duration pulses. Now I'm seeing the time domain. Okay, you have a number of pulses like this. Suppose you have 6,400, so many pulses. Let's say 1,000 pulses. Okay, 1,000 uh, maybe symbols, 1,000 symbols, and the time duration is very less. Time duration is very less because the bandwidth of the signal is large. Okay, bandwidth of signal is large. If I draw the parallel frequency domain, okay, if I draw the parallel frequency domain, if I draw just one symbol here, just this, this one symbol, okay, I'm drawing just this one symbol, it will be having a large bandwidth. It will be having a large bandwidth, right? So remember, I'm just drawing this particular symbol. Okay, that one symbol, it is having a large bandwidth. Why? Because in the time domain the duration is very small, which means in frequency domain you have a large bandwidth. Whereas in multi-carrier, what happens is multi-carrier is more easy to visualize in frequency domain. Let me draw the frequency domain here. In multi-carrier, what happens is this whole bandwidth is divided into small substreams. Let me draw with different color. It will make diagram more clear. Suppose the second substream is like this. Third substream is like this. The substream is like this, etc. So there are multiple subcarriers or multiple substreams, and the frequency is F1, F2, F3. There are center frequencies F1, F2, F3, F4, and the bandwidth of each of the substream, it doesn't overlap with the other substream, which means they are orthogonal to each other. They are not interfering with each other in frequency domain. And for the here the bandwidth is less when compared to it is Bn. This is B. This is B, and here the bandwidth is less when compared to the original when compared to the single carrier communication. And you can see that instead of a short pulse, you will have a pulse with a longer duration. So if this transmission it happened in a, so let's say you have n number of pulses, it happened in t in t in t seconds. T is the time duration of each of the pulse, and you have n number of pulses. So you have the total time taken to transmit all this data is n into t seconds. Here in this case, in multi-carrier, the first symbol, first substream, it will have more time duration, so it will consume all the space. It is having more time duration because it is having lesser bandwidth in frequency domain, so it will have more time duration, and that time duration, let's say it is Tn. Again, the other substream, it is having the same bandwidth as the first substream. The substream which is centered at F2 is having the same bandwidth as the substream centered at F1. That will also have consumed the same time duration because T is proportional to 1 by B. Time duration is proportional to the bandwidth of the signal. And you will have the third substream, which like this, having the same time duration, and the fourth substream, which is again having this time duration, right? And what happens here, this is time. This is time. What really happens here in multicarrier is that here you have short modulated pulses having very small time duration, but here you have a number of pulses which is having a longer duration, but they are transmitted at the same time. Okay, that is the most important thing I want you to note. All streams, all substreams are transmitted at the same time. They are transmitted at the same time. And so what happens is each of these carriers, they get added with each other, right? Each of these carriers, they get added with each other in time, which itself will create certain problems which we will see later. And one of the most important things I want you to note is this time duration Tn. Tn will be exactly equal to n into T. And what was n into T? N into T was the time duration taken by the single carrier communication, and in the same time the multicarrier achieves the same data rate. The same number of symbols are getting transmitted at the same time, but each of the subcarrier, each of the substream, it takes the whole duration of time, and these substreams, they get added with each other in time domain. The substreams get added with each other in time. They get added with each other in time. As a result, in certain places, you have a lot of constructive interference. They add with each other. Okay, if you have 64 substreams, just imagine 64 substreams getting added one over the other, and such a large value of amplitude it is going to come out with, right? So that amplitude is sometimes it is a problem. If it exceeds a particular threshold value, that also is a problem, which is a problem known as PAPR, peak to average power ratio, which we will deal in detail when we are learning the fourth module. So this is precisely the concept of multi-carrier communication. And in multi-carrier communication, you see that these frequencies, they are centered in such a way that each of these substreams, they are having the same bandwidth. They are having the same bandwidth, let's say Bn. Okay, they are having the same bandwidth, and each of these substreams, they are orthogonal to each other in frequency domain. They are orthogonal to each other. In time domain, it is not so obvious whether it is orthogonal or not, but in frequency domain, you can clearly see that the signals are orthogonal to each other. So these substreams, they are orthogonal to each other. So another point I want you to notice, the substreams are orthogonal to each other. All right. Now let me show you the diagram of a multi-carrier transmitter. This is taken from the textbook of Andrea Goldsmith, a professor at Stanford University. The name of the textbook is Wireless Communications. Here you can see the transmitter side of multi-carrier communication. The data comes at a rate of R bits per second. There is a serial to parallel converter which slows down the incoming data stream, goes to a symbol mapper, which is nothing but a modulation device. Okay, it is some type of a modulation. Most popular modulation is either PSK, some PSK, or a QAM modulation. And after modulation, the symbols are you obtain the modulated symbols. You have S0, S1 up to Sn minus 1. These are the modulated symbols. And you have a pulse shaper, that is G of t. So G of t is a pulse shaping, technique. Okay, it is a pulse shaping technique, and mostly the technique used is a raised cosine pulse. Raised cosine pulse. Mostly it is a raised cosine pulse, and after multiplying with the that pulse shaping technique, pulse shaping is done in order for you to have a proper transmission through the channel, such that the pulse doesn't suffer um, any problems that happen due to the sharp edges of transitions in time. And you have S naught of t, which is this symbol multiplied by the raised cosine pulse, and you have here cos 2 pi f naught t, which is a carrier, it is nothing but a carrier. Okay, and what it does is it does a frequency translation. Right? It does a frequency translation. It shifts the frequency to frequency f naught. Okay, and this is very easily you can visualize this in signals and systems. You would have learned that if you have a symbol x of t and you multiply by a quantity e raised to j omega naught t, then in the frequency domain you will have omega minus omega naught, which means if x of t has the Fourier transform or the frequency domain as x of omega, then if you multiply it by e raised to j omega naught t, then this x of omega, it gets shifted by a value omega naught in the frequency. And here you can see you have cos 2 pi f naught t, and cos 2 pi f naught t is equal to e raised to j 2 pi f naught t minus e raised to minus j 2 pi f naught t divided by 2, which means the symbol s naught of t, let me just say it, x of t just gets translated by two frequency values, that is x of omega minus omega naught, and here when it get multiplied with e raised to minus j omega naught, you have x of omega plus omega naught. And in the frequency axis you can see there is a if I draw the frequency axis, if you had s naught of t will get translated by f naught, positive f naught, and gets translated by minus f naught. And this frequency translation, it is nothing but AM modulation, right? AM modulation is a frequency translation technique where you are multiplying the original information signal with a carrier with a higher frequency, and this frequency translation is nothing but AM modulation, or you are shifting it to a particular frequency. And the same happens for the symbol S1 of t, but S1 of t gets shifted at f to a frequency f1 of t, right? F1 of t, and f1 of t is going to be designed in such a way that f1 of t is going to be like this, f1. Okay, s1 of t is going to get so here you have s naught of s naught. Okay, it is frequency domains or not, and this is say s1. So each subcarrier, it carries a particular information having a bandwidth, and again the next frequency comes, then you have f2. Okay, and let's say in order for these subcarriers to be orthogonal, these subcarriers not to be interacting with each other, what is the condition for the frequency sender frequencies f0, f1, f2, etc.? It should be fi. If I denote in general fi should be equal to f naught, that is the first sender frequency, the frequency of the first stream f naught, plus I into bn, where I is equal to 0, 1, etc. up to n minus 1 if there are n number of streams. That is, this is f naught, and f1 is going to be f naught plus bn, which means f naught, and this is bn. This is bn by 2. This small distance is here. This is bn by 2, and this is also bn by 2. So only if you have a separation of bn, you will have no interaction with the two substreams. So the fi should be designed in such a way that it is equal to f naught plus I into bn. f2 is going to be f naught plus 2 times bn, which means this is duration. So this is bn by 2, this is bn by 2, this is bn by 2, and this is bn by 2. So f2 is equal to f naught plus 2 times bn, or you can say f1 plus bn. So the frequencies, each of the sender frequencies of subcarriers should be designed in such a way that you have fi is equal to f naught plus I into bn, where I is equal to 0, 1 up to n minus 1. And the textbook also has shown the frequency domain of different symbols, that is sender frequencies f0, f1, f2 up to fn minus 1, and here they have marked that bn, which is the bandwidth of the substream, it is much less than the coherence bandwidth of the symbol. And here you have s of f. S of f is this. These are your s of f's, which are the substreams which I have drawn now. And the dotted lines, it is nothing but the channel. Dotted line is the frequency response, h of f. It is a frequency response of the channel. And at the sender frequencies, they have shown the frequency response of the channel, which goes like this, and you can observe that the channel is approximately flat for these range of frequencies, or in other words, bn, coherent bn, which is the bandwidth of substream, is much less than the coherence bandwidth of the channel. And this is the multi-carrier transmitter. This is the concept behind multi-carrier communication. And see, all these symbols after modulation, they are added with each other. They are combined and they are transmitted at the same time, which is a diagram they have drawn here. They're transmitted at the same time, right? And I can write the equivalent symbol S of t, which is getting transmitted from here. S of t can be written as summation I equal to 0 to n minus 1 Si, which are the individual symbols, getting multiplied with a pulse shaping technique. Mostly it is a raised to cosine pulse, cos 2 pi fit plus phi I. So f cos 2 pi fits, all these are the different carriers with which signal is getting multiplied. Each of the symbol SIs are getting multiplied with cos 2 pi fits, and this phi I is a phase offset. It is a phase offset of ith carrier. It is a phase offset of ith carrier. So with that, I conclude the discussion of multi-carrier, the concept of multi-carrier communication and multi-carrier transmitter. In the next class, we will see about multi-carrier receiver. Thank you.